Hi students, we're going to talk about section 3.5 today. So you can flip in your book to that. I believe it's page 189. Okay, so we're going to talk about segment addition, the segment addition postulate, and a lot of different proofs that go with segments. So in this figure, point B is said to be between points A and C. So we've talked about that idea of betweenness of points. You can also say that the distance between A and B plus the distance between B and C is equal to the distance between A and C by the segment addition postulate. So we are going to start to use this idea of segment addition postulate quite a bit. And what it's going to allow us to do is to look at a picture like this. So this is kind of that if, and then conclude that we can make a statement like AB plus BC is equal to AC. That's what the segment addition postulate allows. So you see in a picture that diagram and you spit out this step right here with the reason of segment addition postulate. Okay, so determine whether this is true or false is on the side of the page. So if A, B, C, D, and E are collinear with AC equal to 10, B between A and C, you can keep reading through this, then is AB equal to BC equal to DE. So I don't know about you, but as soon as I read that, I'm like, I don't know what that's talking about. So I'm going to write stuff out, and it says B is between A and C, so I'm going to have A, B, and then C. And remember, between does not mean directly in the middle. Then it says C is between B and D, so it sounds like we're going in alphabetical order here. And then D is between C and E, yep, so we're going to keep those in alphabetical order. So I followed these steps here and drew that stuff out. Let's see what else we have here. It says that AC is equal to 10. So from A to C, this is 10 units long. So I drew that part out. And then it says AC is equal to BD. So that means that BD is going to be 10 units long, which is equal to CE. So that also means CE is going to be 10 units long. And the question is AB equal to BC equal to DE? So we have to think through this idea and see what's going on here. So C is definitely the midpoint of AE. Because of those, we have our BD. Is there any way for, so here's how I think about this, is could this be 2? And then this would be 8. And then if that was 8, then from B to D, that would make this 2. And then from C to E, that would make this 8. So that's all possible based on what's given here. So then is AB equal to BC equal to DE? Not necessarily, okay? So this would have to be false, and my counter example is right there. Okay, so you can think through some of those things, but that's the idea of the segment addition postulate. Okay, so we are going to use segment addition postulate to do some proofs, and some of these proofs can get kind of complicated, so we're going to practice with them quite a bit. So write correct statements and reasons to complete this proof. We're starting from, we know QT is congruent to RV, and we're going to prove that QR is congruent to TV, which if we look at the segments, it should make sense that that is true. Okay, so QT is congruent to RV is going to be our given. Then they're going to use definition of congruence, which if we remember, this allows us to either say if congruent, then we have segments that are equal, or we can say if there's segments that are equal, then they are congruent. So we're going to utilize that idea. And if you would rather write it this way, you're welcome to do that. So if congruent, then equal, that is our definition of congruence. But that allows me to say that the measure of QT is equal to the measure of RV. So a quick little change over there. We do that because looking at this proof, it's going to be a segment addition proof. And addition is something that happens within equality, not congruence. So we make that quick switch. Okay, the next thing that you see here is QR plus RT equal to QT. So what I do is come up here, QR plus RT equal to QT, and I look at that as it's a part plus part equal to whole relationship, and that is exactly what the segment addition postulate is. So the reason behind this one here is the segment addition postulate that allowed us to make this statement. And this doesn't come from a statement before it. This just comes from the diagram that's up there. So hopefully the same thing happens here. We have an RT. I'm going to change colors here. Sorry. We have an RT plus a TV equal to an RV. Yep, that is segment addition postulate as well. Okay, so that's what happens there. Now, trying to follow through this proof of what they did on each end here, we have a substitution step that's going to happen in 4. So the substitution is that QR plus RT, which is equal to QT, can substitute in for QT. And then we also have a substitution of RT plus TV, which is equal to RV, and that can substitute in for RV. So that's my substitution that's going to happen here. And so now I'm just going to rewrite it. And so that's going to say that QR plus RT is equal to RT plus TV. And again, what I did there is I did substitution. If you want to, some people like to do this. It was step number 3 that went into step number 2. Okay, so you can mark that if you like to. You do not have to. Just something to help out a little bit. So what they did next is subtraction property of equality. So what you're seeing here is that they subtracted RT from both sides of step number 4. So they took step number 4, rewrote it with a subtraction of RT on both sides of the equation. So once you subtract RT from both sides, that plus RT minus RT leaves just QR there. Plus RT minus RT leaves TV there. So this is a simplify step. Again, you have a few options here. You can say combine like terms. You can say simplify. You can also technically say substitution. It's not my favorite, but you can say it. And then lastly, once we get to QR equal to TV and we want QR congruent to TV, well, we switch that. So this one is definition of congruence, or if you wanted to do an if then, if equal, then congruent is the way that that one would go. Okay, so there's one proof done for us. Now, not every segment addition proof is the same. So what I always talk about is there's kind of 2 ways that these go. If you notice, the given in this case was QT congruent to RV. So QT is a large segment congruent to a large segment, and we were proving QR congruent to TV, which is a small segment congruent to a small. So this is a proof where it goes from like the large to the small. In that sense there, and a lot of those proofs are similar to each other, but sometimes we go from the small to the large, and those just work in a little bit of a different way. So let's take a look at the check that they give us. So here they tell us that CE is congruent to FE, so we can see those, and I can mark them in the diagram if it helps me. And then they also tell us that ED is congruent to EG, so I can mark those as well just to kind of see them. And I'm trying to prove the large segments congruent. So this is what I was talking about, where we're going to go from knowing small segments to proving large segments, and the proofs just look a little different. Okay, so right off the bat, they give us our given, so that should be our first reason that we know there. And then if I look at it and I just say, okay, what's happening here? Well, it just changed from congruence to equality. So this is the definition of congruence that allows us to do that. Or in this case, again, if you wanted to, you could write if congruent, then equal. Again, notice my if is what was before and my then is what I stated here. So we went from step 1 and we used step 1 to get to step 2. So another thing I'll do sometimes is check off steps as I use them, because usually you don't reuse a step. So I use step 1 to say step 2. Okay, then step 3, it says CE plus ED equal to CD. So as soon as I see a plus on there, I'm going to think to myself, either it's addition property, but there's not something added on both sides, or at this point, segment addition postulate's pretty accurate. So CE plus ED equal to CD. That is a part plus a part equal to a whole. So that is my segment addition postulate that is happening there. Part plus part equal to whole. So didn't use any of these statements, just use the diagram in order to state that. And if I look at FE plus EG equal to CD, that is not part plus part equal to whole. So we got to be really careful there. So I got to find something else. So I'm pretty sure I know what I'm going to look for, and I'm going to look to circle something. So here, if I have CE equal to FE, I can take FE and put it in for CE. And ED equal to EG, I can take EG and put it in for CD. So this is going to be a substitution step right here. As I substituted each of those quantities in, rewrote it, FE plus EG equal to CD by substitution. So actually I used step 2 and step 3 to state step 4 that's there. So if you're using the check mark method, you can do that. Then if I keep coming down here, let's see what changed. So that's all the same, but then we have an FG over here. Okay, you know what? I'm going to come back to my diagram for this one. FE plus EG equal to FG. That is my segment addition postulate right there again. And the reason we're going to have done that is because these two are very similar to each other now. So segment addition postulate allowed me to state that. Notice I didn't check anything off. So I'm actually going to use step 4 and step 5 in order to state step 6. So if I look at this, I have CD that was equal to FE plus EG, and so I can put that CD in place of those two things there. So CD is then equal to FG, that's right here. So this was a substitution step as well that happened there. And then last but not least, when you need to switch back to congruence, you can either say definition of congruence, or in this case, if equal, then congruent, because that's what we're trying to state there. Okay, so there's another example of a proof. We also have some segment congruence that comes into this. So if we just kind of quickly look through this, you learn that segment measures are reflexive, symmetric, and transitive because segments with the same measure are congruent. These properties apply to segment congruence as well. So we're just bringing up these ideas again of reflexive, symmetric, and transitive properties that again apply to, and they kind of go through that idea here that they apply to congruence and measurements. And so they're equality and congruence properties as you go through them. So the reflexive property allows you to state that one segment is congruent to itself. Symmetric property states that two different segments can be listed congruent in two different orders. And the transitive property is with comparison of three things. So I always do RST 1, 2, 3 to remember which property is which. If that helps you, feel free to use it. RST 1, 2, 3. That you're going to use reflexive property the most and transitive property the most. Symmetric property will happen when we're using algebraic proofs, but it doesn't happen a ton otherwise. Again, the other thing with transitive property is that if two things, so in this case A, B, and E, F, are congruent to the same piece, so that's C, D, then they're congruent to each other. So either way that you want to read through that, but we have these properties again. A good question that happens on the side here, and if you didn't see it, do take a look at it. Is there an addition property of congruence? The answer to this one is going to be a no, because addition is something that happens with equality. It does not happen with congruence. So if you're going to add together two quantities, then you don't want to be talking about the segments. You want to be talking about the distance of those segments, which would be equality. Okay, because again, like I said, they're all different. Here's another one. Feel free to pause the video and go through it first if you want to. So R is the midpoint of QS. You can see that written here, and T is the midpoint of VS. So there's our givens. The other thing I'm going to point out is that our third given is way down here. And once in a while, that's kind of a strategy that people use, which is totally fine, but just see that it's in there. Okay, so the reason they did that here is because R is the midpoint of QS allows me to state that segment QR and segment RS are congruent to each other right there. And T being the midpoint of VS allows me to state that VT and TS are congruent to each other. These are both by the definition of a midpoint, or you can use your midpoint theorem. There you can also say if a point is a midpoint, then it splits it into two congruent segments. If you like the if thens, that's what you would say. So I kind of use step one to say step two that was there. Then we have our next given, so that's put in there. And then we get to another step. So now we've got to kind of reason through this and think through it again. QR congruent to TS here. So I'm going to look up here and I see QR here, I see QR here, I see TS in here. And so actually this is the perfect thing right here, is that I have these pieces. I'm going to box them in, part of 2 and part of 3. So where I see QR and TS both congruent to VT. And so therefore they're congruent to each other. So this is my transitive property. You're probably going to ask, so no, I do not expect that you write of congruence or of equality, mainly because it does work for both. Okay, so that was my transitive property that allowed me to do that. And then they throw a symmetric property in here. Now this is something that some people use, some people don't. I'm actually going to have us just cross through that and not do it. Some people like the order of them to be the same, but for us, if we look at this right now, I now have this QR congruent to RS up here. Oh, I wanted that to switch colors so we could see it. We have QR congruent to RS up here, and we have QR congruent to TS down here. So since two pieces, RS and TS, are both congruent to the same piece, QR, then they're congruent to each other. And there's our transitive property again that's used here in the end. Okay, so that's another example that we have. Finishing it off here with another one, and this one's a long one, but let's see if we can follow through it. So I always like to find my givens first. So I see GJ congruent to GI, and I'm going to come all the way down here and I'm going to write given because there's where I see it in there. K is the midpoint and H is the midpoint, so I'm going to write given in here because those are kind of those easy ones that we want to fill in. And then I'm going to see what happens. So if I've kind of followed the idea, if we state a midpoint, we're going to state congruence. So K is the midpoint of GJ. So we have GK congruent to KJ. That's right there. And GH is congruent to HI. That's my other midpoint that's there. So these are going to be by the definition of a midpoint. And I can mark those off in the diagram in case I need that as we go through. I then hopefully start to see kind of the pattern, but we have congruence change to equality. So this is going to be my definition of congruence that allows that to happen. So I use step 1 to state step 2. I use step 2 to state step 3. Then I have another given in step 4. And I notice that I'm going to use another definition of congruence in step 5 there. So I use step 4 to state step 5. So if you're following along this proof, step 3 and 4 have not been used. And so hopefully those are going to kind of come into play here in just a bit. So if I'm looking at step 6, GJ is equal to GK plus KJ. This is my segment addition postulate. GK plus KJ equal to GJ, that whole piece. And the same thing with the other one, that GI is equal to GH plus HI. This is my segment addition postulate. So I'm going to fill that in. Again, that came from the diagram. So right now I have step 3, 5, and 6 that are all not using each other at this point. And so we're probably going to run into that right about here. Let's see if we can follow this. GK plus KJ. So I see that right there. GH plus HI. I see that right there. I'm hoping I have GJ equal to GI. I do. So I'm going to take this piece here and substitute it in for GJ, and then this piece here and substitute in for GI, and that's what allows me to get to 7. So step 7 was substitution. And again, if you want to, it's substitution with step number 5 and 6 that we kind of put together there in order to get to 7. And then I'm wanting to get to 8. And if I kind of have an idea of how this goes, usually, okay, the GK stayed the same. So the KJ and the GK, and those are equal to each other here. So I'm taking this GK and I'm substituting in for the KJ that's right there. And then same thing over here, that GH and GH were the same, but HI needed something. So this GH is substituting in for HI right there. And so this is also a substitution step. If you like to keep track of it, it's step number 3 and 7 that just happened there. And because of that, I'm going to check those guys off. So I'm pretty sure I'm just kind of following from there. Continue on, GK plus GK is 2GK and GH plus GH is 2GH. So this is a simplify. You can say substitution. You can also say combining like terms. Okay, so that led us to there. If you don't already have it written down, think about this before I say it as to how this happens. But I look at step 9 and I'm going to divide both sides of step 9 by 2 in order to get to this step here. So this is our division property. If all you write is division, it is wrong. It's a division property that states that I can divide both sides of an equation by the same thing and still have an equation. And that gets me pretty much to the end. So my definition of congruence takes me back to my congruent statement and takes us full circle on that proof. Okay, lots of stuff going on there. The last one is just kind of a thought-provoking question. A city council plans to convert a section of a city block into green space. The north sidewalk is congruent to the south. Okay, so north is congruent to south, which is congruent to the west sidewalk. So the south is congruent to the west. Therefore, it says the north sidewalk is congruent to the west sidewalk. So they're then concluding that the north is congruent to the west, and they're saying what theorem, postulate, or property justifies it. Hopefully you've beat me to it, but the answer to this one is the transitive property. In this case, it would be of congruence, but that's the idea behind that one. Okay, thank you guys very much.